So this is going to be pretty fast. I'm hoping it's 20 minutes or under on ecosystems. So what we're going to be attempting to do is defining how can we define these ecosystems. But rather than talking about the biotic and the abiotic, we're going to look at it from two different perspectives. One of them is through biodiversity. The other one is through a concept called productivity. So we need some background and a little bit of refresher. When we look at an environment, obviously there are biotic and abiotic factors. Those help shape the conditions under which evolution can occur, and more specifically, under which natural selection can occur. Part of those conditions will end up creating competitions or some type of social interaction or a non-social interaction between different organisms, and that also will flavor the way in which organisms evolve within a community. Remember that when we talk about an environment and we have biotic and abiotic factors, that tells you that in an area there's life and there's non-living things. We can give that term for that area with biotic and abiotic factors an ecosystem. When we look at this in terms of a hierarchy, or at least of emergent properties, if we look at one individual, it doesn't mean much. If you happen to have a whole bunch of the same type of individual that can all reproduce, we call that a population. If we have a mixture of different types of populations, meaning they have different things within each of those populations, we create what we call a community. And if we blend that community with its environment, we get what we call the ecosystem. And this is actually the source of the selective pressure. It's the biotic and the abiotic. It's not the environment, it's actually the ecosystem that is truly the selective pressure source. Sorry, I don't know why I'm having issues breathing right now. Oh well. So if I look at it, one of those ways that we can judge is based upon biodiversity. Biodiversity would be how many different types of organisms you happen to see in a certain area. That's easy enough. And there are ways to attempt to quantify it because you can look and kind of say, oh yeah, that's diverse, or oh, that's not so diverse. But it's nice if we can quantify it, if we can put it into a number. And there's several different indices for biodiversity. One of them, which is the one that we're going to use, is called the Shannon Index, which is this big old funky equation. And because I don't wish to assume that you necessarily know all of these terms, just for the sake of pointing it out, this funky E thing here is called sigma. Whenever a sigma shows up, like when we talked about chi-square earlier in the year, all this means is add up everything that shows up after it. So this means let's add up all of these that exist. The I means it's some reference point, which is why it says from I equals 1 to R. So you'd have organism type 1, then you'd have organism type 2, organism type 3. How many organism types are there? There are organism types. So what this means is add up all of these for every single type of organism within this area that we wish to give an index to. P sub I stands for the proportion of that individual. Meaning, if you have 5 species, this is the proportion species 1 is of the total, the proportion that species 2 of the total, the proportion of species 3 of the total, the proportion of species 4 of the total, the proportion of species 5 of the total. So you're going to take the proportion, which is going to be a number somewhere between a 0 and a 1, and you're going to find out that we don't necessarily want zeros because they aren't there, so why are we including them? But something between a number greater than 0 and all the way up to potentially 1, and you're going to multiply that by the natural log, ln natural log, which is log base e, of that proportion. All this does is give you an exponent. So for those of you who haven't done that yet in math, whenever you take a logarithm of some number, you get the exponent that caused it. So if you were to take in your calculator and type in log, L-O-G, and then type in, I don't know, 10, the log turns out to be log base 10. So what it's going to do is it's going to find the exponent that turns 10 to some exponent to equal the 10, the number that you typed in after log. And that, of course, would be a 1. So your calculator will spit out a 1. If you hit log 100, what it's going to try and do is find the exponent that turns or 10 to the something power to equal 100? And that answer, of course, would be 2. Natural log doesn't use the base or the thing that we're trying to find the exponent of as 10. It actually uses a different number, which is e, which is 2.71 something or rather. That shows up in math quite often. Also shows up in science quite a bit too. So we're going to add up all these numbers. We take a negative value of it. I don't really know why we use a negative value of it. I just know that we do. And then we have our value. If you turn out to have a perfectly uniform situation, meaning the proportion is 1, the natural log of 1 is 0, which means a 0 would indicate it is perfectly uniform in terms of the organisms present. The further away we get from 0, the more diverse it would turn out to be. So if we look over time, we have actually seen fluctuations in biodiversity. So it's not like biodiversity is something that remains constant. And one of the reasons why it could fluctuate in part is mass extinctions. If we have mass extinctions or we have major shifts in how the Earth is structured, we're going to have shifts in biodiversity. As easy as that. There are patterns as to where organisms are, where areas are more biodiverse than others, but we don't necessarily need to figure that one out. You could look it up on your own. They're not too hard. There are patterns. Another way that we look at ecosystems is we look at the energy utilization. So, drink water. What we can look at are two things. One of them is called production. The other one is called productivity. They are very similar. Production is how much, while productivity is how quickly did you make that much. Meaning, if I told you that, oh, I graded 100 tests, you go, oh, okay, nice. How long did that take you? Oh, 5 minutes. Oh, okay, which seems a little wonky, but that's okay. So my production would be 100 tests. My productivity would be 100 tests in 5 minutes. So the big difference between the two is productivity has a time component to it. When we look at an ecosystem, there are a whole bunches of things that we have to think about. One of them is what we call gross primary production or productivity. Doesn't really matter which one, although typically we talk about it in terms of production. Gross means the overall. That is a fancy word for photosynthesis. So we have all sorts of energy that's produced by plants. The catch is the plant's not going to get to keep it all. Some of it is going to be lost through respiration, while other bits of it can hold on to and then use to grow the plant, or it can reproduce or something like that. When I have my total, my gross, which is photosynthesis, and I get rid of the part that I have to get rid of, which is respiration, I'm left over with what we call net primary production. The net primary production is what the plant gets to keep. And this turns out to be the equation. Gross primary productivity, when you get rid of the respiration, gives you the net primary production. It's kind of like when you get a job that's not under the table. So if you make, $100,000 in the year, that's your gross. If you have $40,000 of taxes, your net would be $100,000 minus the $40,000, which is $60,000. Your net income would be $60,000, while your gross income was $100,000. There is a difference between the two. There's part that you have to get rid of no matter what. The thing is, we care about more than just plants, so we can actually look at how it moves from one organism to the next. When you go away from plants, so you're eating a plant, the biomass that accumulates in the thing that ate the plant is what we would call secondary productivity. If you then go and eat that rabbit, you would then be a product of secondary productivity or tertiary productivity, or production. This actually is using, since there's no time component, productivity might not be the best term, might be production, and I fell for it. The thing is, the rabbit's going to eat the food. It's not necessarily going to consume everything, so there's going to be a loss in the consumption. There's going to be a loss with metabolism. There's going to be a loss because some of it's not going to be digested and it's going to fall out. So even then, all the food in here, the net from the plant, is not going to show up in the rabbit because we're going to have a whole bunch of losses, and whatever is left behind turns out to be the secondary production or productivity. I assume, for those of you who took APES, that you did the lab where you figured out biological dissolved oxygen. It's not too hard. If we were to look at dissolved oxygen around the world, and a way you can kind of sort of judge it is based upon chlorophyll, or how much, how many plants you turn out to have that can actually undergo photosynthesis. And what we get are patterns of dead zones, where if you look, purpley areas and bluish areas are kind of saying, it's not that great, and red is saying, holy cow, this is amazing. And then obviously you have ranges in between. When we look, there are some patterns in terms of concentration and how dense things turn out to be. But the part that makes it rather interesting, at least to me, well, there's a few. It's, there's high concentrations in deserts, yet they're not necessarily that productive. And when we look at the ocean, there's not much there. Yet if we look at where most of the oxygen is formed, it actually turns out to be in oceans. And the reason for that, actually, sorry, I was reading back and forth between these things. Here, if there are plants, they're going to be actually really, really dense with chlorophyll, but they have other issues. But when you look at the oceans, they're actually kind of dead zones. And we would think that, oh, well, that's not so good, except that with oceans, they actually do an amazing job at producing oxygen. And the reason for that is there's just so much ocean. So figuring out dissolved oxygen, parts per million of oxygen, turns out to sometimes be misleading. Within an ecosystem, we have to deal with energy, obviously. So we can deal with it in terms of productivity or production. The catch is, you could figure out how good an ecosystem is based upon how energy flows. And this is something that we call an energy budget. So we're going to have something that flows in. We have stuff that flows out. What flows out is always going to be heat. We're going to have stuff that gets lost, which is going to be heat, or things that don't get fully digested. And the result of that is we get less and less energy throughout the system. Hence, we have that 10% rule. And if you sit there and you could follow along, figuring out how much energy flows in, how much is being lost as heat, how much is being lost as waste from undigested food, you can actually start to figure out the energy efficiencies and actually see, is it a 10% rule? Is it not a 10% rule? You could do this for an entire ecosystem, much like how you could do it for an individual organism. So we could look at how much food goes in, we could see how much is lost in terms of respiration, we could see how much is lost through feces, and whatever is left over turns out to be the change in the biomass or the body mass or its production. So we can actually sit there and measure all of these things and figure out how efficient certain organisms are. And what we find is not all organisms turn out to be built the same. They're not all 10%. Some are better than 10%. Some are much, much worse than 10%. But you have that in your worksheet, so I will leave that to you. And it has been about 20 minutes. So go me, got it on time.